Learning Goals. Welcome to this learning session on soil, forest, and climate change. In this course, we shall address Introduction to Resource Conservation, Forestry, Management, and Agroforestry Systems. Soil, Meaning, Properties, and Importance. Climate Change, Causes and Food Impacts. Mitigating Climate Change and Resource Management. There will be a quiz at the end to test your knowledge.
Introduction to Resource Conservation. This section introduces the critical interconnections between forests, soil, and climate change in agricultural production. Understanding these relationships is fundamental for sustainable food systems and natural resource management. We will explore the importance of forestry, forest management, and agroforestry systems. Additionally, we will delve into the composition and properties of soil and the effects of climate change on food production. Forestry and management. Defined forestry is the art and practice of managing forests and woodlands to achieve specific objectives. These objectives include protecting biodiversity, ensuring timber production, and supplying essential ecosystem services. Forest management involves planning and applying practices to optimize forest productivity. This includes making informed decisions about forest use, protection, and restoration. Importance of forests. Forests are crucial for environmental protection, supporting diverse plant and animal species, and providing wildlife habitats. Proper forest management helps preserve these vital ecosystems and their biodiversity. They also act as significant carbon sinks, absorbing atmospheric carbon dioxide and moderating climate change. Well-managed forests enhance carbon sequestration, contributing to global climate change mitigation efforts. Forests regulate water flow, improve water quality, and reduce flood and drought risks. They also provide sustainable timber, recreational opportunities, and support local economies through jobs and forest products. Principles of forest management. Sustainable forest management ensures current resource use does not compromise future generations. This involves wise use, reforestation, and protection to maintain forest health and productivity. Biodiversity conservation protects the variety of forest plants and animals, maintaining ecological balance and benefits. An ecosystem approach manages forests as interconnected systems, considering all components for health and sustainability. Community engagement involves local communities and stakeholders in management decisions, respecting traditional knowledge and livelihoods. Adaptive management requires regular evaluation of forest conditions and practices, making adjustments based on new information. This section explores forest conservation practices and the importance of certification. Learn about maintaining healthy forests through various management techniques. Conservation of forest soils involves good management practices to prevent damage and erosion, crucial for clean water and plant growth. Fire management includes preventing and controlling wildfires, sometimes using planned burns for forest health. Timber harvesting and regeneration practices ensure forests recover naturally with minimal ecosystem damage. Forest certification involves third-party verification that management practices adhere to accepted sustainability standards. For example, the Forest Stewardship Council (FSC) certification ensures timber products come from responsibly managed forests. This helps consumers make environmentally conscious choices. Forestry and agriculture interrelations. The interrelations between forestry and agriculture highlight their close and diverse relationships in terms of land use. They often share space and mutually benefit, making sustainable land use planning essential. Integrated landscapes with farms near forests boost biodiversity, improve local climate, and protect soil. Forests also benefit from pollinator movement and enhanced soil nutrients from nearby agricultural areas. For instance, forests provide vital ecosystem services like pollination and pest regulation to adjacent farms. This symbiotic relationship underscores the need for holistic land management strategies. Agroforestry practices and systems. Agroforestry integrates trees with crops and/or livestock on the same land, enhancing productivity and environmental resilience. It involves careful planting and management of trees alongside farming activities. Common practices include alley cropping, agri-silviculture, trees in rows with crops between; silvopasture, trees combined with livestock grazing; windbreaks, trees shrubs along field edges to reduce wind speed. Other systems are agroforestry gardens, household gardens with diverse plants; Tongia system, temporal crop cultivation with tree seedlings; forest gardens, mimic natural forests with food-producing trees and shrubs. Meaning and importance of soil. Soil is a natural body composed of minerals, organic matter, water, and air, serving as a medium for plant growth. It also supports the life of various organisms. Essentially, soil is the Earth's upper crust, comprising mineral particles, organic matter, water, air, and living organisms. Its quality directly impacts agricultural productivity and sustainable food production.
Soil's agricultural importance. Soil is the primary source of essential nutrients like nitrogen, phosphorus, and potassium for plant growth. It stores and releases these nutrients, vital for healthy crop development.
It acts as a reservoir, holding water for plant roots during dry periods, ensuring continuous growth and drought resistance. Soil also provides stable anchorage for roots, enhancing plant stability and nutrient uptake. Furthermore, soil facilitates aeration and gas exchange, allowing oxygen uptake and carbon dioxide release for root health. It buffers against extreme pH changes, maintaining a stable environment for roots and microorganisms. Soil profile, layers and characteristics. A soil profile is a vertical cross-section revealing distinct layers or horizons, each with unique characteristics. These horizons are denoted by letter symbols and provide insight into soil formation. The typical profile includes O horizon, organic layer; decayed organic matter, humus, dark brown black; E horizon, topsoil, mineral particles, organic matter, microorganisms, primary for plant growth; E horizon, alluviation layer, leaching of clay, iron and minerals occurs here. Further layers are B horizon, subsoil, formed from A horizon weathering, lower in organic matter; C horizon, parent material, weathered rock, sediments or glacial deposits; R horizon, bedrock, unweathered consolidated rock, barrier to root growth. Importance of soil profile. Knowledge of the soil profile helps assess soil fertility and nutrient status, guiding farmers on appropriate fertilizer application for increased crop productivity. It also aids in identifying drainage characteristics, informing irrigation practices. Understanding the profile assists in nutrient management by revealing nutrient availability, pH, and microbial activity. This allows farmers to tailor practices for optimal nutrient absorption and crop suitability. Furthermore, soil profile knowledge helps determine erosion susceptibility, crucial for implementing control measures. A deep, healthy profile supports better root penetration, enabling stronger plants to access more nutrients and water. Physical properties of soil. Soil texture, the proportion of sand, silt, and clay particles, affects water retention, drainage, and aeration. Sandy soils drain quickly, while clay soils retain much water but drain poorly. Soil structure refers to how particles aggregate into clumps, influencing water movement, root growth, and microbial activity. Well-structured soils allow for better plant development. Porosity, the percentage of pore spaces, affects water infiltration and air circulation, benefiting root health. Bulk density, the mass per unit volume, indicates compaction. Higher density restricts root growth. Chemical properties of soil. Soil pH measures acidity or alkalinity, ranging from 1 to 14. Values below 7 are acidic, above 7 are alkaline, and 7 is neutral. pH significantly impacts nutrient availability for plants. Cation exchange capacity, CEC, is the soil's ability to retain and exchange positively charged ions like calcium and potassium. High CEC means more nutrients are available to plants over time. Nutrient content refers to the presence of macronutrients, N, P, K, and micronutrients, Fe, Cu, essential for plant growth. Organic matter content, from decomposed residues, provides nutrients and supports microbial life. Determining soil properties. Field methods for assessing soil properties are crucial for informed agricultural decisions. Soil pH can be determined using litmus paper or a portable pH meter, with color changes indicating acidity or alkalinity. Organic matter content is visually assessed by dark coloration and crumbly texture. Soil structure is evaluated by digging a pit or using an auger to observe aggregate size and shape, such as granular or blocky forms. Soil texture is determined by feeling wet soil between fingers, gritty for sand, sticky for clay, and smooth for silt. Porosity is inferred from texture, with sandy soils being highly porous and clay less so. Soil components and importance. Soil is composed of several key components, each vital for its health and function. Mineral particles, derived from weathered rocks, form the soil's texture, influencing water-holding capacity and aeration. Organic matter, including decomposed plants and microorganisms, enhances soil fertility and supports microbial activity. It also plays a crucial role in carbon sequestration, mitigating climate change. Water is essential for nutrient transport to plant roots and biochemical reactions in microorganisms. Air in pore spaces is critical for root respiration and aerobic microbial activity, promoting organic matter decomposition. Climate change, meaning and causes. Climate change refers to long-term shifts in weather patterns, temperature, and ecosystem disruptions. It is primarily driven by human activities, particularly the release of greenhouse gases, GHGs, into the atmosphere. GHGs like carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O, trap heat, leading to global warming. These gases originate from burning fossil fuels, deforestation, industrial processes, and intensive agriculture. The increased concentration of GHGs intensifies the greenhouse effect, causing Earth's atmospheric temperatures to rise. This warming has far-reaching consequences for global ecosystems and human societies. Effects on food production. Climate change negatively impacts crop yields through altered temperature and rainfall patterns and extreme weather events. Heat waves, droughts, floods, and storms damage crops, reducing productivity and causing failures. Rising temperatures can disrupt pollination processes and decrease crop quality. Shifts in growing seasons alter planting and harvesting times, affecting crop development and suitability in various regions. Water availability changes due to altered rainfall patterns, leading to shortages or excess water. This impacts irrigation, causes waterlogging, and increases soil erosion, further threatening agricultural productivity. Climate change significantly impacts agricultural systems. This section explores the effects on pests, diseases, and the resulting consequences for food prices. Climate change influences the prevalence of pests, weeds, and crop diseases. Warmer temperatures and altered climatic conditions create favorable environments for increased infestations and crop damage. Changes in temperature and rainfall patterns can also affect beneficial insects, disrupting natural pest control mechanisms. This leads to shifts in pest dynamics, making crops more vulnerable. Climate change-related disruptions contribute to reduced crop yields and supply chain disruptions. Reduced crop yields, supply chain disruptions, and higher demand drive up prices, exacerbating food insecurity globally. Mitigating climate change impacts. Mitigating climate change effects on food production requires developing and promoting crop varieties resilient to temperature fluctuations, drought, and pests. This includes investing in research for climate-smart farming techniques. Implementing sustainable soil management practices, such as conservation agriculture and agroforestry, improves soil health, water retention, and nutrient availability. These practices enhance soil's ability to withstand climate shocks. Monitoring and early warning systems are crucial for prompt detection and response to pest and disease outbreaks. Promoting integrated pest management, IPM, reduces chemical pesticide use, relying on natural control methods instead. Water and livestock management. Efficient irrigation techniques, like drip irrigation and precision irrigation, reduce water wastage in agriculture. Developing and improving water storage systems, including rainwater harvesting and small-scale reservoirs, is also vital. Promoting water use efficiency and conservation practices among farmers, alongside adopting drought-tolerant crop varieties, enhances resilience. These measures ensure stable water supply in changing climates. Enhancing livestock management practices, such as improved housing, feeding, and health management, mitigates heat stress and disease risks. Promoting sustainable aquaculture and strengthening marine conservation protect aquatic food sources.
Summary. Well done, you have completed the course Soil, Forest and Climate Change. You should now be familiar with Introduction to Resource Conservation, Forestry, Management, and Agroforestry Systems. Soil, meaning, properties, and importance. Climate change, causes and food impacts. Mitigating climate change and resource management. Should you need to revisit any of the topics in this course, please use the menu at the bottom of the screen.